Welcome, everybody. So I'll be talking about foundations of homomorphic secret sharing. And let me start by talking about secret sharing in general. Okay, so this is a sort of a core fundamental question that's studied within cryptography. And kind of the first thing that you always learn in the crypto class is additive secret sharing. Okay, so suppose that I have some secret group element, S, that I'd like to split across two different people. Okay, in such a fashion that okay, you have to visualize here on your own. Okay, so in such a fashion that each of these two different group elements here individually hide the secret S. And on the other hand, if I take the two elements together, they have an additive reconstruction. Okay, so if you think about it for a couple seconds, a possible construction here is just to choose S0 completely at random and have S1 be the appropriate value to give you reconstruction. Okay, so the topic of today is going to be sort of an extended version of this, a homomorphic secret sharing scheme. And here we think of a similar setting. So I have some element X that I want to split into two different parts here with a similar sort of secrecy guarantee. Okay, but a bit of a side note here, we're going to consider two possible different types of secrecy. So when I refer to statistical secrecy, this means that really, if I see just an example, this is statistically distributed independently of what the original X was, versus the notion of computational hiding, where this is just saying for computationally bounded, say polytime bounded adversaries, that given a single share, you can't tell whether this came from some X or some X prime. Okay, so the homomorphism comes in at this stage, and this is saying that for some function f, say described as some program or circuit of some sort, that given a single share, I can locally homomorphically evaluate a function f, such that these output shares, this y0 and y1, have some form of reconstruction. Okay, and for today, I'm going to consider two different types of reconstruction. The first is the analog of additive from the previous slide, where I just need to take y0 and y1 and add them up to get the desired evaluation f of x. And in fact, so maybe this might sound a bit restricted, but this specific type of reconstruction will have a lot of interesting applications. But even more generally, if I want to relax this notion and just say I'm allowing an arbitrary reconstruction function here, but in order to make this, this notion non-trivial, say I put a restriction on the size of the output shares. Okay, so this is a succinctness or compact output share restriction. Okay, so this, take you a look, remember this is going to be your friend for the next 20 minutes. Okay, and a bit of a comment here. So note that this F, this is coming from somewhere. And when you talk about a homomorphic secret sharing scheme, this is with respect to some class of functions, a supported homomorphism class. Okay, so for example, you can think about the class even just of linear transformations, okay? And in that case, even the original additive secret sharing scheme you saw in the original slide already gives you some form of homomorphism. Okay, so for today, though, when I'm talking about homomorphic secret sharing, I'm going to be talking about more general types of homomorphism classes and things that don't have such a nice kind of automatically homomorphic structure. Okay, so think about, for example, I want to be able to support any function that's represented as an NC1 circuit. Okay, so first, and actually I think, especially for a general crowd, one of the things I really want to convey is why this is a really cool area. And there's a lot of fascinating questions that we'll talk about a bit later. But one of the things, so why am I so interested in this? Because homomorphic secret sharing has a lot of cool applications in cryptography. So as a tool in order to build a bigger system. Okay, and just kind of to give a bit of a flavor of this, two different types where this appears and gives kind of surprising even results. The first is a type of use in private database queries and manipulation. Okay, so for example, if I assume I'm in some setting, I've got a database that's stored, say, copies of the same database on two non-communicating servers. I can actually query the database, say, for position I, or some more complex queries of this database by sending information to each of the different servers, getting something back, and in such a way that neither of the servers actually learn anything about what I'm querying. Okay, and so homomorphic secret sharing, and by the way, I'm going to keep calling this probably at some point HSS. So HSS constructions give us really actually surprisingly lightweight solutions for this to the extent that people are implementing these things and running on AES and building systems. Okay, something that's maybe a little bit higher, more on the theoretical side of things, is in the notion of secure computation. Okay, so suppose the secure computation, what do I mean here? Suppose that we have two parties, each with some secret input. Okay, I have x, you have x prime, and we want to jointly learn the output of some function f on x and x prime, but without revealing the input. And in fact, without revealing anything about your inputs beyond what is revealed by the output f of x comma x prime. Okay, so this is a beautiful area of cryptography. And since the 80s, we know that there actually are ways that you can do this for any function f. But something that's kind of interesting, a barrier that we keep running into, is that even, for example, if f has very short inputs and outputs, but the circuit itself is very large, if we don't care about security, you can communicate, you can learn f of x comma x prime by a very small amount of communication. But if you do care about security, then up until somewhat recently, the only way that we knew how to do this still required communication comparable to the circuit size. Okay, so when I refer to succinct secure computation, I mean something that's sublinear in the circuit size. And really, to date, there's only two solutions. There's only two ways that we know as a community how to achieve this. One is by a tool known as fully homomorphic encryption, and the other one is via homomorphic secret sharing. Okay, so kind of more a second just targeted to more of the crypto crowd. So if you are familiar with fully homomorphic encryption, a little bit of trade-offs, or what do we get that's better or worse? So in the first category, you do have to lose a little bit of something in the sense that you have to assume these non-communicating servers. But on the flip side, you have a lot of really nice, much more efficiency properties. For example, you get optimal compactness here. The information that's sent back is something very short as opposed to a long ciphertext. Okay, and in both of these categories, compared to fully homomorphic encryption, you can get this on more varied assumptions. Okay, so hopefully you're convinced this is the coolest thing ever. So let me give you a little bit of an overview about what we know right now about this in the crypto community. Okay, so what exists up to now, and by the way, I should mention that aside from simple types of homomorphism, things like linear functions or a few things that are implicitly implied by like locally decodable codes, homomorphic secret sharing for more expressive function classes have really only been studied up to the last couple years. Okay, so at this point, we have this kind of jumble of different related but not quite the same definitions. So for example, you saw already you can consider different types of reconstruction. Maybe you've also heard the phrase function secret sharing. This is almost isomorphic to homomorphic secret sharing, but we're kind of a dual version. And in this last slide, I was actually cheating a little bit. You'll see that this thing becomes a little bit more complicated. But this is a version of sort of multi-input homomorphic secret sharing, where I'm assuming that different clients can use the secret sharing, but homomorphism can go across clients' inputs. Okay, and we have a handful of positive results and kind of a handful of limitations. And just kind of to flash in front of you, what do we know? So for example, so this represents the class of homomorphisms that are supported. And you can kind of roughly separate this into two categories. So down here at the bottom, for very, very simple function classes, things like point functions that are zero everywhere except for a single hidden input, we have constructions from one-way functions. Once you get up to something like in C1 and above, we have this based on decisional Diffie-Hellman and learning with errors. And by the way, so here this is even on top of fully homomorphic encryption. Okay, and the only negative results sort of that we know, that if you have an additive reconstruction, then basically anything non-trivial, you're going to require some sort of computational assumption. So one-way functions are kind of the minimal here. And once you get up to something like a C0 and C1, then this has implications to succinct secure computation. So for example, in particular, it has to imply a notion known as oblivious transfer. Okay, so I'm coming kind of to the end here. I want to start narrowing more toward what we're going to focus on in this talk. Okay, so for all these different results and so forth, I want to think about this And I should mention there's really quite a horizon, lots of different landscape of notions and things that could be studied and understood. But for today, I want to focus just on these 2x2 category. So where reconstruction is either additive, you just add the shares together, or this more general compact output shares, and a single input versus a multi-input case. Okay? So this, don't worry too much about all these letters, especially if you're not a crypto person. But I want to emphasize a couple different things where we still have rather big gaps. So here this represents that we know, for example, that this notion requires at least one-way functions, and we have, based on different richness of the function classes, we have constructions based on various computational assumptions. Okay, but for example here, I really wish that this worked, but I'll just jump, okay? So for example here, we know that this multi-input additive reconstruction category, we can build it from these highly structured, specific assumptions, but the only thing that we know that it implies is kind of this lowest level of general assumption that implies secure computation. Okay, so for things like public key encryption or maybe oblivious transfer itself, it's not clear whether we could try to get that. Are we just, you know, being lazy or can't figure this out, or is there really a limitation here? So I'm hiding a lot of stuff. For example, so each of these different assumptions are for a different function class. Okay. Okay. And in addition, so how about if you go up to this multi-input compact output shares? So here in this implication to oblivious transfer, we can show that you can get basically secure computation if you have this additive reconstruction. And kind of the punchline is that secrecy comes because of the additive reconstruction, okay? Because that means that if we're exchanging our shares at the end, then I'm not learning anything. So seeing your share, I could have simulated just by knowing my share and the output, okay? It's just the sum of these things. And as soon as you lose that, as soon as you go to a more general reconstruction where you're just putting a requirement on the size, we have no idea. Maybe this could even exist unconditionally. Maybe you could get this with statistical security with no computational assumptions, okay? Okay, so for this work, this paper, we sort of initiate a more foundational study of this notion, trying to map out the landscape and see what sorts of relations do we have. Oh, really? Oh, wow, okay, well, you are not gonna see much of our results. So we give a definitional framework. In terms of this box from the previous slide, we show two different, this is the bad news that we need to mention, two different lower bounds. So we show that for compact and multi-input, that you cannot achieve this without requiring some sort of computational assumption. And we show down here, we boost this, so from oblivious transfer, which is a nice general assumption, to what's something that's known as non-interactive key exchange. And the point here, don't worry about what it is, but the point is that this is a highly studied notion. It's been studied for, okay, like decades. And to date, we still, even for this notion, don't have constructions aside from things based on similar flavors of specific structural assumptions. Okay, so this kind of gives a partial justification for why we've been stuck at this. Okay, and then we give two different applications. The first is an application that if you have homomorphic secret sharing for a specific simple function, then you can plug this in and get a really low round complexity, so 2-round secure computation protocol for any function. And the final one is an application to worst case to average case reductions in P. Okay, so this is clearly delusional, but let me see what I can get through. So this, I was hoping to do the negative results and a bit about average case, worst case reduction. Okay, so first of all, just really quickly, the first part is looking at this multi-input notion of HSS. And again, what is this? So this says that multiple clients can share their values, and you can homomorphically evaluate across them to do some sort of reconstruction, okay, of two different types. Okay, so the first claim, and maybe this will be what I hope to get through. Okay, so suppose that you have such a notion at all, okay, with compact output shares. And by compact here, my threshold is going to be that it's less than the communication complexity of the function f. Okay? then we show that you cannot hope to achieve statistical security, that you have to have some sort of computational assumption. Okay, so to do this, let's kind of take a step and think about how can we use HSS in order to get some sort of communication protocol for the function f. Okay, so say that Alice and Bob have respective inputs at x and x prime. Okay, so think, for example, something you might do is secret share each of your inputs, keep your share and send the other share to the other individual. Okay, and then do a local homomorphic evaluation and have, say, Bob send his output share to Alice. Okay, so this is a bit silly so far because the communication complexity here, in order to exchange these input shares, could potentially be a lot of communication. Okay, but note that up till now we've only used the correctness property of HSS, and now somehow we're going to need to use the fact that there's security, and not just security, but statistical security. I want to somehow remove this first round of interaction, and I'll do it as follows. So think about having shared randomness between the two parties, okay? And this is public randomness. And what this is going to be essentially the shares that we would have exchanged on the previous slide. Okay, so this you have already. And the point is that because you have statistical security, that means that given basically a random or share or an arbitrary input, that I can reverse sample, I can find a second share that's consistent with my input. Okay, so for example, Alice, there's xb that's in the sky, that's not something she's choosing, but from that and her input x, she'll generate x sub a. Okay, and from there, the rest basically follows. Okay, so now we have the shares. We didn't actually have to communicate anything. And then you locally homomorphically evaluate and just have to send the output share. Okay, so this collectively here gives a communication protocol for the function f. And the communication was just the size of one of these output shares, y sub b. Okay? And even kind of an observation here that this is not even just the communication complexity, but even one-way communication complexity. So collectively, this says that if you have a function f, something like inner product or set disjointness that has high communication complexity, then you can't hope to get non-trivial HSS. Okay, so how much time do I have? Okay, great. Okay, so let me actually, I'm going to skip to the good news. This is all fascinating stuff. Ask me about it later. Okay. So good. So let me say a little bit about how you can use HSS in the application of worst case to average case reductions in P. Okay, so suppose I've got some function f, and I want to be able to worst case evaluate it. And suppose, so an assumption that there exists a homomorphic secret sharing scheme for the function f. Okay, so what does it look like? We've seen this picture before. Okay, so what's interesting about this thing is that this is giving me a way of transforming my x into two new values, x0 and x1, that by the secrecy property of the HSS, essentially are independent, or maybe computationally independent from x itself. Okay, essentially these look like some sort of random values. And what does that mean? If I look at this, I zoom in on the eval function, this eval sub f, call this some function f prime. Okay, this means that if I can evaluate f prime on average, well, in particular, then I can take my worst case x and split it into these two average case inputs. And this can allow me, so using this box, to reconstruct f on x. Okay, so as an application here, plugging in known existing constructions of homomorphic secret sharing, this gives us conditional, for example, average case hardness for fine-grained complexity. Okay, so for example, and I should give a bit of a caveat, this is definitely a hand-waving version. You should take a look at the paper for the really complete theorem statement. But kind of, morally, if you have HSS for circuits, and you have some sort of language, say, that can be computed in time n to the c, but is worst case hard in time n to the c minus epsilon, then this HSS gives the existence of a new language, L prime, whose computation is roughly the same as the original L. but which is now average case hard for n to the c minus some epsilon prime. Okay? So, so kind of comparing what, for example, how does this compare to some of the things that came up earlier in Guy's talk? So these two works give a similar sort of average case hard function using fine-grained complexity. And kind of in comparison, we have the stronger assumption. We're assuming that you have homomorphic secret sharing for some function class. And this is a computational assumption. But then our result ends up being stronger. So they show this for specific structured functions, and this is for any function. Is that inherently this reduction, if you use fully homomorphic encryption, this function that you get, this L prime, so say you start with a function and you get a new function, even if your original function f was a Boolean function, f prime necessarily had long output, or you'd have to do lots and lots of queries to this function. And you have, say, additive HSS, then this new function, f prime, will also be a Boolean function. Okay, so just to conclude, in this work, we unify and we extend various definitions and notions of this thing. We give two pieces of bad news, these limitations in the multi-input HSS setting. And we give two types of applications. I didn't get a chance to talk about secure computation. It's actually kind of that field has developed even since here. So there's interesting trade-offs. And we give these applications to worst case to average case reductions in P. All right? And that's it.